Hello everyone. Here is our next question of computer organization from the topic instruction pipelining that we are going to solve today. This question was asked in the year 2005 for 2 marks. The question is, a 5-stage pipelined CPU has the following sequence of stages: instruction fetch from instruction memory, instruction decode and register read. So the operand fetch or register read is combined with instruction decode here. Execute, data memory access, register write back. So these are the 5 stages. Consider the following sequence of instructions. Instruction 1 is a load instruction, LR0 location 1. What it means is the value at the location 1 is read from the main memory and loaded in R0 register. Instruction I2 is an arithmetic operation, AR0 R0. What it means is the value of R0 is summed up with itself and the result is stored back in R0. I3 is another arithmetic operation, AR2 R0. What it means is the value of R0 is subtracted from value of R2 and the result is stored back in register R2. So the question goes further. Let each stage take 1 clock cycle. What is the number of clock cycles taken to complete the above sequence of instructions starting from the fetch of I1? So we need to calculate the total number of clock cycles that would be taken by these 3 instructions. So here what is not given is whether we should consider operand forwarding or not. So as by considering operand forwarding, the number of clock cycles that would result would be lesser and it is more efficient. So we would consider the case of operand forwarding for answering this question. But for our knowledge purpose, we would also see the case where we would calculate the number of clock cycles required by these instructions without using operand forwarding. So here the thing that should be noted here is that instruction I2 is dependent upon instruction I1, because instruction I1 is reading the memory location LOC1 and then loading that particular value in R0, and I2 is using that new value of R0 for calculating this, for performing this arithmetic operation, whereas I3 is dependent upon I2 because I2 is producing a value, modifying the value of R0, and that modified value of R0 is used by I3 for performing this arithmetic operation. So the conclusion is I2 is dependent upon I1 and I3 is dependent upon I2. Right? So because of this data dependency, data hazard might occur, and to resolve that or to lessen the number of stalls, we can use operand forwarding. So we are going for operand forwarding to solve this question, and examiner is also looking for the solution considering operand forwarding. But as I promised that we would later part of the video, we would also see the case where the number of clock cycles would be calculated without using operand forwarding, and we would equip ourselves with the knowledge of that also, so that for some other problem, if sometimes it comes in the next question paper, we can attempt it. Well, so let us draw a clock cycle diagram and attempt this question. So I rub this off for the emptying some space for explanation. So let us draw a clock cycle diagram. Let's say C1 is the first clock cycle, C2 is second clock cycles, likewise C3, C4, C5, C6, C7, C8, C9. Hope this would be sufficient for solving this question using operand forwarding. So when I say using operand forwarding, what is the difference between the case where we use operand forwarding and we don't use operand forwarding? So if we use operand forwarding, the consumer instruction means the instruction that is consuming the value produced by a producer instruction. So this is a producer instruction here, and I2 is consuming the value of R0 that is produced by I1, so I2 is consumer instruction. So in case where we are using operand forwarding, the consumer instructions execute stage didn't have to wait till write back stage of producer instruction has occurred. In case when we are not considering operand forwarding, the register read stage as well as the following execute stage has to wait till producer instructions write back stage has occurred. And in case of operand forwarding, the execute stage of the consumer instruction didn't have to wait till that long till write back stage of producer instruction has occurred, but it has to wait only till the point where the value on which it is dependent or the value which it requires it produced by the producer instruction somewhere in the pipeline. So we would go in details by drawing this diagram, and I would explain it to you little further. So as I1 is the first instruction, it would occupy the first 5 cycles to complete. So instruction I1's instruction fetch would occur in C1, followed with stage instruction decode and register read, followed with execute, memory access, and write back. So these are the 5 stages for instruction I1, and in C5 it would get completed and leave the pipeline. What about instruction I2? So instruction I2's instruction fetch would occur here without any issue, and as we are considering the case of operand forwarding, as we are using operand forwarding, so its register read and instruction decode can also occur in C3 without any problem. Had it been the case where we were not using operand forwarding, this register read has to wait till write back stage of the previous instruction or the producer instruction has already occurred. So in case of without operand forwarding, this register read stage has to wait till C6, right, until and unless the new value of R0 is written by I1 in R0 register in the write back stage, the register read cannot occur in the case without operand forwarding. But here we are using operand forwarding, so register read or instruction decode and register read can occur anywhere. So in C3 it can occur. Execute stage has to wait till the new value of R0 is produced by the producer instruction. So here it is a load operation, and only after memory access stage the new value of R0 would be produced by the instruction I1. So only after this stage the instruction I1 would go to main memory and read the value and bring it here. So the new value of R0 would be available at this point, and this point we can call it as point of production of the value on which instruction I2 is dependent, right. So at this point the instruction I1 would produce the new value of R0, right. So execution stage of I2 has only needs to wait only till this value is produced, and after that it can be scheduled. So execution stage of I2 can be scheduled at this point, that is in the cycle C5, because its dependency on this value, new value of R0, has been met. So followed with memory access stage, followed with write back stage. So in cycle C7 I2 would complete its job and leave the pipeline. What about I3? I3's instruction fetch can occur in C3, and with the similar explanation as the register read instruction decode stage of I2, we can schedule the instruction decode register read stage here in C4 for I3. But execute stage of I3 would not occur till its dependence on the new value of R0 produced by I2 is met. So the point of production at which the new value of R0, that is by summing up the values of R0, summing up the value of R0 with itself, is produced by I2 somewhere in the pipeline, and that point is this point, that is at the output of arithmetic logic unit. The new value of R0 would be made available by I2. So this is point of production for the value required by I3. So this is point of production that is required by R3. This is point of production required by I2. So after this point, execute of I3 can be scheduled. Anyway, other reason is the execute of I3 cannot be scheduled here because I2 at this point is in execution stage and arithmetic logic unit is already occupied by I2. So arithmetic logic unit cannot be given to I3 for execution. So definitely it has to wait till this cycle, and at this point the arithmetic logic unit is also free, and also the input value that is required by I3 is available in the pipeline, so it can take it directly from here, right? So this value can be forwarded to arithmetic logic unit. Here also this value can be forwarded to arithmetic logic unit's input, right? And after this, after execution, memory access and write back stage of I3 can occur. So overall there are 8 cycles which would be required by this 3 instruction using operand forwarding. So the correct answer would be 8. So as I promised, I would also talk about the case where operand forwarding would not be used. So as I said, the difference between the using operand forwarding case and not using operand forwarding case is that the register read, in case where we are not using operand forwarding, the register read of the consumer instruction has to wait till write back instruction of producer instruction has happened, because till this point the new value would not have got written in the register. So the register read would read some stale value of R0, right? So I2's RD stage has to wait till C6, till the new value has been written in R0 by I1. So RD would occur here, followed with execution stage, followed with memory access, and followed with write back stage of I2. With a similar explanation, the instruction decode and register read can occur, I3's register read can occur only after write back stage of I2, because after write back stage of I2, the new value of R0 would have got written in R0 by I2. So RD of I3, RD stage of I3 would occur in cycle C10, followed with execution in C11, followed with memory access in C12, followed with write back in C13. So 13 cycles would be required where we are not using operand forwarding. So see, the 13, this option is nowhere in the given options, so definitely we had to consider the operand forwarding method. Hope you have understood the logic. Thanks for watching.